Folks. In this next section of Chapter 8, we are going to examine questions where there is a b value in the quadratic function being graphed. So we've already looked at stretching a quadratic function by having a value for a that isn't just 1. By having a value for c that isn't just 0. And today we're focused on that b value. So let's jump right in and see what we get. Finding the axis of symmetry and the vertex. So to this point, all the examples that we've looked at did not change our axis of symmetry. Our vertex was always along the y-axis somewhere. Maybe it was raised, maybe it was lowered, but it was still on the on the y-axis. And so now we're changing this. And there's a handy dandy formula for helping us determine where that axis of symmetry is, and that is x equals negative b divided by 2a. So if I'm given a quadratic function here, my a value is 2, my b value is 8, and my c value is negative 1. And I can calculate my axis of symmetry as being negative b over 2a, which is just going to be negative 8 over 2 times 2, which is negative 8 over 4, which equals negative 2. So my axis of symmetry is going to be the line x equals negative 2. To find the vertex of the parabola that follows this function, remember, the axis of symmetry has the same x value as the vertex point itself. So if I want to know the exact coordinates of the vertex, all I need to do is plug this x value into the original equation. So my y value is going to be 2x squared plus 8x minus 1. So I'm going to plug in negative 2 where I see x. To negative 2 squared plus 8 times negative 2 minus 1. Well, negative 2 squared is 4, and 4 times 2 is 8. 8 times negative 2 is negative 16, and we subtract 1, and we end up with negative 9 as our y value. Therefore, the coordinates of the vertex are negative 2, comma, negative 9. So this formula, x equals negative b divided by 2a for the axis of symmetry to get us that x coordinate for the vertex is really very handy. And then we can use that information to graph the rest of the parabola. Let me show you how to do that. So if you fully want to graph a parabola that has a b term in it, let's practice doing that axis of symmetry again. I want to graph the parabola, but my first step is going to be to find that axis of symmetry and then to use that axis of symmetry to find and plot the vertex. So I'm going to say that x equals negative b divided by 2a. So I'm going to have negative 6 divided by 2 times 3. So I'm going to have, let's see, negative is a positive. So I've got positive 6 in the numerator divided by 6 in the denominator. So my x value is 1. Now I want to find my y term, my y value for the vertex. So I'm going to input this x value, x equals 1, into my original equation of 3x squared minus 6x plus 5. And I'll replace all of my x's with 1's. And 3 times 1 squared is just 3. 6 times 1 is just 6. And add the 5. So adding all of that together is 2. So if my x value is 1 and my y value is 2, then my vertex ends up being here on the graph. And now I have a base from which I can choose to test additional values to plot on the graph. Um, so one obvious example would just be to test the value 0. That's typically one of the easiest values to plug into the equation. So I'm just going to kind of list other values of x and find out kind of the output value so I can put them on the graph. So I know that the input of 1 gives an output of 2. We've already done that. Let's go ahead and test that input value of 0. So what happens when I input 0? I end up with 3 times 0 squared minus 6 times 0 plus 5. And notice that my first term kind of disappears. My second term disappears because both got multiplied by 0. And I'm left with an output value of 5. So I'm going to move over here. And when my input is 0, my output is 5. Now, here's where the symmetric feature of a parabola really comes in handy. Every time you plot a number that isn't the vertex, so long as you know where that value is relative to the vertex, you automatically get a free bonus point that's on the other side of the axis of symmetry. So I know my axis of symmetry is here when x equals 1. And I've just plotted a point to the left of the axis of symmetry. So I can plot an equivalent point to the right of the axis of symmetry. So I also know that when I'm at the x input value of 2, that I have an output value of 5 as well. At this point, I can see that I do have this kind of stretch value of this multiplication factor of 3. And so if my subsequent points are just going to be off the page here. So I'm just going to go ahead and graph my parabola as best I can. Okay, with the 3 points I have. I typically like to plot 5 points, but that's the best I can do in terms of fitting onto this page here. So we're using the feature of parabolas being symmetric to help us plot get more information about the graph using less work. Let's look at another example. Um, does the function f of x equal negative 4x squared minus 24x minus 19 have a maximum value or a minimum value? And then find that value. These are two new definitions for today. A minimum value is going to be the y-coordinate of the vertex of a parabola that opens upward. So it'll have a minimum value down here. And the maximum value is going to be the y-coordinate of the vertex of a parabola that opens downward. So we're talking about the peak, the maximum of a downward facing parabola. So if you need to find max and min values, really what you need to find is the vertex. And then from the vertex, you determine the y value for that min or max. The other thing you need to do is you need to consider, well, is the parabola opening upward or downward? And the key there is what we learned on the first day in this chapter, which is the coefficient of the first term in the polynomial, that a value that's attached to the x squared term. That is going to let us know whether the parabola opens upward or downward. So because my a is negative in this example, this parabola opens downwards. And because the parabola opens downward, my parabola has a max value. And now that I know I have a max value, I can use my formula x equals negative b divided by 2a to calculate the information that I need about the vertex. So my negative b, I would need to have negative 24. And my 2a is 2 times negative 4. So I end up with positive 24 divided by negative 8, which is negative 3 as my x value. And I take that x value and I plug it back into the original equation. So y equals negative 4x squared minus 24x minus 19. And I plug in the value negative 3 in every time I see x. And I get negative 36 plus 72 minus 19 all adds up to positive 17. So I have a max value at negative 3 comma 17. Let's look at a real world example. This Mackinac Island Bridge in Michigan. This suspension bridge has cables that form a parabola shape between the two pillars. And that parabola is modeled by this function here. And x and y are both measured in feet according to this equation. And we are supposed to estimate and interpret the minimum value of the function. So I want to know the minimum value here. Um, so I'm going to follow the same procedure, even though this is a real world problem. I'll just do x equals negative b divided by 2a. So my b value is negative 0.37. So I've got negative 0.37 divided by 2 times 0.000098. So I end up with positive 0.37 divided by let's see, I'll just plug this into my calculator and I get 1,887.755. I'm going to just round that off to 1,888 feet. Round it off to the nearest foot. And now I'm going to take that x value, plug it back into the original equation to find out what my y value is at 1,888 feet. So remember, this is in the x direction. Basically, I'm talking about being here. I'm this far in from the pillar, 1,888 feet in horizontally from the vertical pillar. So I plug that value into the original equation, 0.000098 times 1,888 squared minus 0.37 times 1,888 plus 552. And I will plug all of that into my calculator in one step, and I'll get 202.765 feet, which I'll round off to the nearest foot, which will be 203 feet. And this is how high I am above sea level or above lake level. So those suspension cables are 203 feet above the surface of the water. Lastly, another real world example. A group of friends is launching water balloons. The function f of t equals negative 16t plus 80t plus 5 represents the height of the first water balloon t seconds after launch. So I'm going to have negative 16t squared plus 80t plus 5. And I'll do balloon number 1 in kind of red here. And then the height of the second water balloon 2 seconds after launch is shown in the graph. So this is water balloon number 2. which I'll represent in blue as we go along. And we want to know which water balloon reaches the height. So we're really asking about the max value. And it's easy enough to tell this from the graph here, or at least approximately read it from the graph. If each kind of marking on the graph represents 25, then this is maybe, this mark would be 125, and we're maybe another 5 above that. So let's say that the max value here is about 130 feet for balloon 2. To find the max value for balloon 1, I need to use the formulas that we've been using for all of the other equations so far. I need to know that the x value is negative b divided by 2a, so negative 80 divided by 2 times negative 16, which means I'm doing negative 80 divided by negative 32, which works out to be positive 2.5. And then I take that 2.5 and input it back into the original function, and I have that my y value equals negative 16 times 2.5 squared plus 80 times 2.5 plus 5. And that's negative 100 plus 200 plus 5. So that works out to be 105 feet. So balloon number 1 goes 105 feet into the air. Balloon number 2 goes 130 feet into the air. And so we can see that balloon 2 reaches a greater height. I hope this helped.